Welcome everyone to the starting of this new chapter, which is called Kinematics. So, in this chapter, we are going to study how particles move and how big bodies uh, are when projected in space, uh, what is their trajectory, what is their path, and how a car moves in a straight line, and things like that. One way, good way uh, of visualizing that what we're going to study is imagining. Let's say uh, there is a lizard which is on a vertical wall, and it wants to get to a mosquito which is in its visibility. So the lizard would start moving in a straight line. So that is called motion in one dimension. That is one part of the chapter, that how do we study particles moving in a straight line. What is the velocity of the particle, what is the acceleration of the particle. And the advantage of studying particles moving in a straight line is that we can actually uh, visualize how what is the position of particle, and we can actually visualize what is the velocity of particle, what is the acceleration of the particle, and how these particles influence each other in a very simple term. Next, imagine the same lizard, but it's now just moving in some random fashion on the wall. Then that means that okay, now we have to associate two coordinates with that lizard, that is x and y. So in that case, its motion would become two-dimensional. So that is what we are going to study in this chapter. That how particles move in a one dimension, how particles move in two dimensions, or even if let's say the lizard falls off the roof, then the lizard would be moving in three dimensions. So all these motions can be studied by using again three terms, which are the fundamentals of the chapter. The first term, which is important, is the position of the particle, and next the velocity of the particle, and lastly the acceleration of the particle. So as you would have already studied in your junior classes, that what these terms mean a little bit. That the position of the particle means that where the particle is at. The velocity, it loosely means how fast the particle is moving, and the acceleration means how fast the velocity of the particle or the speed of the particle is changing. So in this particular chapter, we want to build upon those ideas which we have already studied, and we want to go to the mathematical core of that ideas. That how do we define them, and how do we apply those ideas in different situations. So the first topic which we are going to start off is a frame of reference. So what is a frame of reference? The frame of reference is something which is a simple x-axis, y-axis, and z-axis. So here we have drawn x-axis, y-axis, and the z-axis. So x, y, and z, these are three mutually perpendicular axes which intersect at origin. So this is our frame of reference, and we put a clock with it, and this becomes a frame of reference from which we can study motion of any body or any particle which we can imagine. And it's a convenient point, or we can say absolute point in space, from which uh, studying motion of two or more particles becomes convenient. Next, what is the position of a particle? So position of a particle is what is pretty important. Uh, for a particle moving in a straight line, let's say any particle, so it's moving in some straight line. So let's say the particle is initially at x is equal to 0, and it wants to reach some x is equal to 3 by moving in this straight line only. So this value of x is called the position of the particle. So when the particle goes from x is equal to 0 to x equal to 1 to x equal to 2, we say that the particle is getting displaced and its position is changing from x is equal to 0 to x equal to 3. So this value x is called the position of the particle. Now what if the particle is moving in 2 dimensions? A particle is moving in 2 dimensions, then we require two coordinates to signify the motion of the particles, that is x comma y. Now one thing which we can elaborate upon is that let's say if the particle is actually moving in a straight line, then how far can the line go? So this line can go up till infinite, and also the position of the particle can be negative. So for a single particular line, yeah, single straight line, uh, the value of x can be varied, and this value of x eventually shows how far the particle is from the origin, or whether it's in the negative x direction or in positive x direction. For example, the particle could be somewhere here at -2. Okay, moving to the 2D case. So if let's say we want to study a particle which is moving in a plane, then what we say? Then we say that okay, we can use a vector to represent the position of the particle. So we already know the vector representation of a particle or of a point whose coordinates x comma y. So we knew that we already learned that we have to draw a vector which starts from the origin and which ends at the point x comma y, and this whole vector becomes the position of the particle. So this vector is called the position vector, which we learned in vectors. So this position vector would be called the position of the particle, which is written here. That is r vector. So r is a way of representing the position of the particle, that is xi plus yj, whatever units we are using for this particular system. So let us take an example. So a fly is moving from 2,3 meters to some 4,5 meters in a plane. So we want to write the initial position of the fly. The initial position of the fly, that is ri vector, is equal to xi plus yj. This is what we learned, that if the particle is at 2,3, then the position vector is simply the xi cap plus yj cap. So the x coordinate, that is 2 I cap, plus the y coordinate 3 j cap. So this is the initial position of the fly, which is moving in a plane. And finally, the fly goes to 4,5. As the particle gets to 4,5, uh, we can say the new position of the particle is 4 I cap plus 5 j cap, and this is its final position vector represented as RF. So here not only we want to learn how to represent the position of a particle as a vector, but we also learn how to denote the position of the particle. For example, initial position would be denoted as Ri, and the final position can be denoted by Rf. As we can see, the fly is moving in space with time. So the position of anything which usually moves in space is time dependent quantity. So how do we represent that the position of particle depends upon time? So for one dimension, what we say is that okay, we write the position of the particle, which is the dependent quantity, and we put a curved bracket like this, and we put time within the brackets, and we say that the independent quantity, time, the independent quantity is put within the bracket. So at some particular time, the position of the particle would be represented by this, that is t. So at t equal to 1 second, the position of the particle would be when we put 1 over here. So this represents that the position of the particle depends on time. When we are writing something like this, that is x as a function of t, it is spelled as x is a function of t. So this means that the position of the particle is dependent on time, where time is the independent quantity which we decide that at what time we want to find the position of the particle. So the position of the particle at t equal to 1 second, that is what we want to study. So we said that we would have to put t equal to 1 in this equation. So when you put t equal to 1 here, we realize that the position of particle at t equal to 1 would be simply 1. So this is equal to 1. Next, what is the position of particle at t equal to 3 seconds? So we put t equal to 3, the position of particle is simply 1. As there are no units involved, we can write any unit which we want to, or simply write unit. Okay, next let's do a question. So from this question we would learn how to find the position of particle. Position of particle in terms of time is written as this equation, that is 2t plus 1. So like we learned that we have to put the value of time in this part of the equation to get the value of time. So position of particle at t equal to 1, we would get by putting value of t equal to 1 over here. So when we put value of t equal to 1 here, we would get 2 plus 1, that is 3. So the position of particle at 1 second is 3. Now let's say we are going to put the value of t equal to 2 seconds. So we put 2 seconds here. So we would get 2 into 2, that is 4 plus 1. So that's the position of particle at 2 seconds. That's 4. So as you can see, to represent the position of particle at particular time, we substitute the value of time here, and to represent that the position of particle is 3 at 1 second, we put the 1 over here, so as to complete the idea which we want to represent. Next, we want to express the position of particles in vector form. That is, we want to write the position of particle which we have written already here in vector forms. So particle is in x-axis, so we would say that the position of particle, let's say x vector sum, at 1 second is simply 3 cap, because it's in x direction. Position of particle at 2 seconds is some 5 cap. So next we come on to how to write the position of particle in 2 dimensions. So we know that here we have to just write xi cap plus yj cap. So it is given to us in the example that the x coordinate of the particle is t square and the y coordinate of the particle is simply t. So the x coordinate of the particle as a function of time, this is what this represents. So this is written here, and the y coordinate of the particle as a function of time, this is what this represents. So what is the position of particle at t equal to 1 second and 2 seconds? Position of particle, that is r vector, is xi. Now x is t square I cap plus tj cap. So we put the value of t here. So when we substitute value of t here, we would get 1 square plus 1 j cap. So this would come out to be I cap plus j cap, since this is simply 1 and 1. Next, we put value of time t equal to 2 seconds over here. Then when we substitute value of t equal to 2 over here, we get 2 squared, that is 4 I cap plus 2 j cap. Okay, next question. A particle follows a path r is equal to t square minus 1 I cap plus t square minus 32 plus 2 j cap. Find the position of particle at start of motion, that is 0 seconds and 2 seconds. So here also the idea is that okay, we want to find the position of particle at some particular time, that is 0 seconds. So we know the position vector. Though here the position vector would be looking pretty big, but the idea is to just substitute the value of t. So the value of t is 0 seconds. So we substitute value of t over here. So we get the position of the particle r vector. Now since we are going to calculate at some particular time, we would also like to put 0, that is position of particle at 0 seconds. The 0 substituted here gives you minus I, and 0 substituted here would make this term 0, this term 0, and only 2 would remain, that is simply 2j cap. So that means the position of particle at 0 seconds is minus I plus 2j. Position of particle at 2 seconds is 4 minus 1 I cap plus 4 minus 6. We substitute value of 2 here, so that would be 6 plus 2 j cap. 4 minus 1 is 3i plus 0 j cap. So that means at t equal to 2 seconds, the particle is at 3i plus 0 j. Find the time at which the particle in the previous question crosses the origin. So we know that the particle is moving in some particular direction uh, as given by this equation. The question number 4 asks that when would this particle cross origin? So the particle will cross origin when both the x and y coordinate become 0. So let's put these values to 0. The x coordinate is t square minus 1. So we put t square minus 1 equal to 0. This would give values of t equal to plus minus 1. And uh, the y coordinate t square minus 3t plus 2 equal to 0. So on factorization, you would get the values of t to be 1 second and 2 seconds. So clearly from intersection of these two values, you can see that at t equal to 1 second, that is when we substitute t equal to 1 second, both x and y coordinates would become 0 and the particle would cross origin. So the answer of this question would be t equal to 1 second, that is at 1 second the particle would be at origin. Okay. In question 5, we want to know that a particle moves in a straight line as per r vector is equal to some 2ti, and the position of particle is already given to us. But this position is given to us with respect to origin, that is x equal to 0. What is required is that to write an equation for the same particle if its position is observed from 2i cap. So it is given in the figure that x equal to 2, that is this point. This is going to be our new frame of reference. So from this we want to study what is the position of particle which is falling to the I cap. So as a rule, we can remember that if we want to write some particles position in some new frame of reference, so here we are representing that uh, new position as r dash vector, and to find that particle's position in new frame of reference, what we do is that we take the earlier position of the particle, that is 2p I cap, and we subtract the position of a new frame of reference, which is 2 I cap, from the original position of the particle. So we have subtracted 2 I cap from the original position of the particle, and this will give us the position of the particle in new frame of reference. In new reference. So the rule to be remembered is that you have to subtract uh, the position of the new point of reference from the position of the particle. So this is how we study the position of the particle. That we put the values of time again and again in the position, where the position can be a single dimensional position like we studied in the earlier questions, or it can be two dimensional position. Next we move on to the next idea. So the next idea is displacement. So displacement is something where the particle is something which we study when the particle moves from some one point to another, and it has a particular way of defining it. Now you may be already knowing this definition on your own. So the definition of displacement is the shortest distance between initial and final position, along with a direction from the initial to final position, because we have to make displacement as a vector, and it must contain the information that in which direction the particle actually moved. For example, if I say that the displacement of the particle is 2 meters, then it does not say that the particle moved in some, let's say, north direction or northeast direction, or upwards or downwards. For example, there is a honeybee which is flying. So we won't say that the particle or the honeybee is moving 2 meter in north direction. It would be moving up and down also. So that complete information has to be enclosed. So we define displacement as the shortest distance between initial and final position, along with the direction in which the displacement has happened. That is the direction from initial to final position. So how do we write a displacement? So the writing of a displacement can be done by this alternate definition. That is, we subtract the initial position of the particle from the final position. That is x2 minus x1, something like this. And it need not be vector even. For example, for a particle moving in straight line, we say that the displacement of the particle is simply x2 minus x1. So x2 minus x1, this is called the displacement of particle when it is moving in a straight line. When the particle is moving in two dimensions or some more than two dimensions, we have to use a vector. So even then the idea says the same, that the final position of the particle minus initial position is called displacement of the particle. So what we have done is that we have written the initial position of particle, some general initial position x1i plus x2j, and some final position of the particle, that is x2i plus y2j. So the displacement of the particle is equal to final position minus initial position. So that is x2I plus y2j minus x1I plus y1j. So x2 minus x1 I cap. This becomes the position or displacement of the particle. We just gather the I cap components here. The I cap, x2 has a positive sign in front, x1 has a negative sign, the x2 minus x1. Similarly, y2 minus y1. So this becomes the displacement of the particle. If we want to draw a graph and we want to see how the particle's displacement vector is there, so let's say a particle has traveled from some point A to some point B along this path. So what is the displacement? The displacement is the shortest distance between initial and final point along the direction, which makes it a vector. So to calculate displacement, we only need to know what is the displacement along x-axis, that is delta x, and the displacement along y-axis, that is delta y. So delta x I cap, displacement along x-axis, delta y j cap, displacement along y-axis. And when we combine the displacements along x and y-axis, we get the net displacement of the particle which we want to find. So one thing which we would like to emphasize in displacement is that it's a vector. It's basically summarizing, we say that it's final position minus initial position. Most importantly, like we saw here, it is independent of the path taken between initial and final point. Since it's a vector, so it does not depend upon the path which we have to. Let's say a particle starts from origin on a straight road, crosses the milestone 2 meter and 4 meter kilometer subsequently. Find the displacement of particle between the milestones. So between the milestones, the displacement of the particle would be final position minus initial position. Final position of the particle is 4 km. Initial position of the particle is 2 km. 4 km minus 2 km. This is the final position of the particle. The final displacement of the particle plus 2 kilometers. A particle follows the path x equal to 2 root 2 meters, where t is in seconds. Find the displacement of the particle between 1 second and 4 seconds. So here the position of particle is given as some equation in terms of time. So we substitute values of t to get different positions. So the final position is obtained by putting value t equal to 4. So we would get xf equal to 4 meter. When we put t equal to 1 second, which is the initial time, we would get x initial equal to 2 meters. The displacement is simply 4 minus 2, that is plus 2 meters. Now the displacement in one direction shows a sign also sometimes. When the displacement is positive, that means the particle is moving in positive x direction. When the displacement is negative, then the particle is moving along negative x direction. Now let us come to two-dimensional example, where we are going to actually do something new, where we are going to apply the knowledge of vector to find displacement. So a particle moves as per this equation. R vector is equal to a cos omega t I cap plus sin omega t j cap, where a and omega are constants of some appropriate units and time is in seconds. Find the displacement of the particle from 0 second to t equal to pi by 2 omega seconds. So between these two times, we have to find how much the particle has displaced itself. So as you can see, it won't be easy to imagine how the particle is moving following two trigonometric equations in two different dimensions. But with the idea of displacement, what we can say is that we can simply substitute value of times to get the initial and final positions of the particle. So the initial position of the particle can be found by putting t equal to 0 in this equation. So when we put t equal to 0 in this equation, what we would get is that t is equal to 0 in cos omega t and t equal to 0 in sin omega t. So this becomes cos 0 I cap plus sin 0 j cap. The initial position of the particle then becomes a I cap, where cos 0 is 1 and sin 0 is 0. Then we have to write the final position of the particle. The final position of the particle, we would have to substitute t equal to pi by 2 omega. So when we substitute t equal to pi by 2 omega in this value, we get cos omega into pi by 2 omega I cap plus sin omega into value of time pi by 2 omega j cap. So what we have done is that we have put value of t where the variable is there, and then we are going to solve it further. This is all we have done. So as you can see, when we put value of t in omega t, uh, the omegas cancel out. The omega and omega cancel out here and here, and the remaining argument within the cos function is simply pi by 2, cos pi by 2 I cap plus sin pi by 2 j cap. The cos pi by 2 is 0 and sin pi by 2 is 1. So this is 0 I cap plus j cap, and final position would be simply a j cap. Initial position of the particle is cos 0 is 1 and sin 0 is 0. So this is a I cap. The displacement of the particle is simply final position minus initial position. So that becomes a j cap minus a I cap. So taking a as common, we have a j minus I, or we can rewrite it as I cap minus j cap, as is the convention to write I cap first and j cap later. So after doing this example, we move on to some questions. A particle moves as per x equal to t square. Find the displacement of the particle between t equal to root 2 seconds and t equal to root 3 seconds. So we have to find the displacement of particle. So again, following the same steps. First, we write the initial position of the particle. The initial position of the particle is written by substituting the value where the particle is initially. The particle is initially at t equal to root 2 seconds. We substitute root 2 in our equation, which is t square. Squaring value of t, that is root 2 squared, gives us simply 2. And similarly, writing the final position, root 3 squared. Root 3 squared is simply 3, and the displacement of the particle is simply final position minus initial position. That is 3 minus 2, that is 1. A particle moves as per x equal to t square. Find the ratio of displacements of the particle in first, second, third seconds of motion. So let us find the position of the particle at different times. After first second, the particle is at 1. After second, the particle is at 4. Third second, since these are squares, simply we can write squares, 16. Now, if we look at the wordings of the question, it is required of us not to write the ratio of positions, but the ratio of displacements of the particle in first, second, and third seconds of motion. The displacement of the particle in first second of motion would be how much? That would be displacement between 0 second and 1 second. So at 1 second, the position of the particle is 1. So displacement between 0 and 1 becomes simply 1. Again, displacement of particle in second. The displacement of particle in second would be the difference of the position of particle at t equal to 2 and the position of particle at t equal to 1. The difference of position of particle at t equal to 2 and t equal to 1 is simply 4 minus 1, which is 3. Similarly, finding the displacement of particle in third second would be the difference of position of particle at x equal to 3 and x equal to 2. When we are talking about some nth second or third second or second, we want to find the displacement in a time interval. So that means that between t equal to 2 and 3, t equal to 9 and 10. So when we are talking about third second, that means t equal to 2 and t equal to 3. So that difference is 5. So as you can see, this is a series of odd numbers. So it gets 7 next and so on. So the ratio of displacement would be 1 is to 3 is to 5 is to 7 and so on. So this would be a ratio of odd numbers. Now third question. The position of particle is given by r vector is equal to e की power t I cap plus sin omega t j cap. Find the displacement of particle between 0 second and pi by 2 omega. Okay, so for that we have to write the initial and final position of the particle. So just making some space. Yeah. So now the initial position of the particle can be found how? By substituting the initial time, that is 0. So we substitute t equal to 0 over there. We get e to the power 0 I cap plus sin omega t, that is sin 0 j cap. E to the power 0 is simply 1, that is simply I cap. And the final position of the particle uh, can be obtained by substituting pi by 2 omega in that particular time. That would be e to the power uh, pi by 2 omega I cap plus sine. When we substitute pi by 2 omega in this, would get simply sine pi by 2 j cap. So the final position would be e to the power pi by 2 omega I. Sine pi by 2 is 1, and that is j cap. So the displacement of the particle would be final position minus some initial position, which is simply I cap. So the displacement of the particle, we write final position minus some initial position, that will be e to the power pi by 2 omega minus 1 I plus sine pi by 2 j. Consider an xy plane in which a particle is moving. The north direction represents y and the east direction is x. A particle moves 10 meter east and then 20 meter north. We have to find the displacement of the particle. So let us draw x-axis and y-axis. The particle moves 10 meter east. That is along x direction it moves 10 meters. And along y direction it moves, that is along north, it moves 20 meters. Since it is moving along north, we said y-axis and not the other way around. So it is given in the question that it is moving 20 meter north. That's why we said that the particle is moving 20 meter north direction. Uh, we have to find what is the final displacement of the particle. So we can write a vector to represent this displacement. That would be a very convenient way, and that is the whole point of vectors. Then when we are given cases like particle is moving east or north, then we can use vectors to simplify those problems which would otherwise require us to think in differently. So like here we know that the particle is moving 10 meter along x-axis. Then we would say that okay, the displacement of the particle is 10 meter I cap plus 20 meter j cap. So that would be the displacement of the particle. For question number 4. A boat sails 4 kilometers east, turns 30 degrees towards south, and travels 5 root 3 kilometers. Find the magnitude of displacement of the boat in complete motion. Now, this is the problem for analytical addition of two vectors, where the boat has traveled some 4 meter or 4 kilometer east and 5 root 3 kilometer in this particular direction. The angle is 30 degrees. So that is as it is written as it is written here, that it turns 30 degrees in south direction. So if this is east, then we know that this is north and this is south. So after traveling 4 kilometers east, it turned 30 degrees towards south and traveled 5 root 3 kilometers. So we want to eventually calculate this complete displacement. So we say that the displacement of the particle delta r is equal to a square plus b square, that is 4 square plus 5 root 3 square to ab, that's 4 into 5 root 3 cos 30 degree root 3 upon 2 to the power half. 4 square is simply 16 plus 5 square is 25 times 3, that is 75, plus root 3 times root 3 is 3. So 5 times 4 times 3 is 60. So this would come out to be 151 to the power half meters. Last question for this particular idea of displacement is that a boy walks 5 meter west. It turns right and walks 4 meter. Then it turns right again and walks 1 meter. We have to find the position of the boy with respect to its initial position. So let us draw a figure. North, east, west, and south. So let's say the boy walks 5 meter east or 5 meter west. So it has moved a distance 5 meter along west direction. It turns right. So now from the frame of reference of the boy, we would see that if it has to turn right, then it would then turn from west to the northward direction. So it would be facing this north direction now after it has turned. So after turning right, it walks 4 meter. So it has walked 4 meters in this direction. Then the question says that it turns right again. So it would now be facing east direction and it walks a distance of only 1 meter. So we know that if it would have traveled a further 4 meters, then it would have reached the vertical line where it started from. So this the remaining distance is 4, and the vertical distance it has traveled is also 4. So what is the position of the boy with respect to initial position? The position of the boy with respect to initial position would be this particular vector. So we can write this vector as some -4 I cap plus 4 j cap. That would be one way of writing the position. Another way would be to define what direction the boy is in. So the boy is in northwest direction, and what angle is that direction making with west? So this distance is 4 and this distance is also 4 since the boy has moved 1 meter back. So this angle would be 4 upon 4, that is tan theta would be 1, or the angle would be 45 degree. The angle is 45 degree, so this can be called northwest. So the boy has traveled this much distance, which would be 4 root 2. That is, the boy is 4 root 2 meter northwest of its initial position. Okay, so in displacement we saw that writing the position of particle as a vector gives us many advantages. For example, in the last question we simply wrote -4i plus 4j to represent the position of the particle. And here, when the motion of the particle itself is pretty complicated, here the x-axis is following some what do you say, some exponential path, and the y coordinate is following some trigonometric path. Even in those cases, without even drawing the path along which the particle is moving, we can find the displacement of the particle by substituting the values of t in the particular function at different times. So to summarize, we can say that the displacement of the particle uh, is the final position of the particle minus the initial position of the particle, and because of that definition itself, the displacement of the particle is independent of the path taken between those points. Next, we talk about speed. Now, after discussing uh, where the particle is at and how we are going to measure the new position of particle from its initial position of particle. Now we want to talk about how fast the particle is moving between the initial and final position, which path along which it is going to travel. So to talk about speed, we must remember distance. So we must be knowing distance already. Distance is simply the path taken by the particle or the length of the path of the particle along which it is moving. And average speed is defined as the ratio of the total distance of the particle and the total time taken by the particle. Uh, so because of its definition itself, average speed or speed becomes a scalar quantity, as distance is a scalar quantity, so speed is also a scalar quantity. What could be the unit of speed? So the unit for displacement of position was simply meter or centimeter or kilometers. The unit for speed can be meters per second or kilometers per second or kilometer per hour. So that can be exercise for you at home, that how much is 1 kilometer per hour is in meters per second. So that is 5 upon 18 meters per second. So find it yourself. So let us move on to an example of studying what is average speed or reviewing what is average speed. So in this example, we are given that a man starts walking with the speed of 1 meter per second for first second of motion, 2 meter per second for second of motion, and so on. Find the average speed for first 5 seconds of motion. So if we read it again, it is given the speed is 1 meter per second for first, 2 meter per second for second, and so on. That means that this is an increasing or diverging series where the speeds are increasing depending upon what second of motion it is going to be. So if it is going to be third second of motion, then it's going to be 3 seconds, 3 meter per second for third second of motion, and 4 meter per second for fourth second of motion. Now, it is important to remember that we are talking about the second of the motion and not for 3 seconds of motion. That is, when we are saying that the speed is 3 meters per second for third second, that means that it's particular second for which the speed exists and not for the complete 3 seconds. So how do you find the average speed? So how much distance would I have traveled in the first second? That would be 1 into 1. How much distance in second? That would be 2 into 1. In the third second, 3 into 1. Fourth second, 4 into 1. Since the time interval is only 1 second. So the distance traveled up till 5 seconds would be 1 into 1 plus 2 into 1 plus 3 plus 4 plus 5 divided by the total time taken. So that is the definition of average speed, total distance upon time. So that would be 1 plus 2 plus 3 plus 4 plus 5 divided by the total time 5. So that would come out to be some 3 meters per second. Moving on. A car travels with speed v1 for first half and with v2 speed for second half of a time interval, and the average speed for whole motion. So this is a pretty standard question when we're studying average speed, that how to find average speed for whole motion. So for first half, the speed is v1. Let's say the total time of motion is 2t. So the speed for first half of motion is v1. So we would say v1 into t is the distance traveled in first half of motion. v2 is the speed for second half of the motion. Then we would say that v2 into 2 is the speed for the second half of the motion. The total distance of the particle is then divided by the total time taken by the particle, which is 2t. So the total distance divided by total time would give us the average speed for whole motion, which would come out to be v1 plus v2 divided by 2. That is the average of the speeds in the both motion, would be the average speed for whole motion. Next, what is a car travels with the speed v1 for x distance, with speed v2 for next x distance, find the average speed for whole motion. In this particular question, we are going to calculate time. So this would be a common idea in all the questions, that we always look for the unknowns given in the question. Unknowns are not given in the question. For example, in first question, it was not given that how much distance was traveled in first part of the motion. See, we look for that. Obviously, we have to look for the final part of the question. That is what we want to achieve. But that is the process of finding the answer in any question. The answer of any question would rarely come out in a simple F equal to ma form, that you put m and mass and acceleration of a body, then you get the force acting on the body. We have to always look for the unknowns in the question first before proceeding to the eventual value which we want to calculate. So with practice, we would know that what are the unknowns which are much more important rather than others. For example, when we are talking about kinematics, the unknowns which are important are time and position, and the unknowns in the eventual quantity are to be determined to find whatever the quantity is. That is, for example, in average speed, the unknown quantity is time. That information for time is not given in the question whatsoever. So that is our focus going to be, that what is the time taken by the particle in first x distance? What is the time taken by the particle in second x distance? No matter what the calculation is, yeah, no matter what are the conditions in the question, that has to be the focus in the question. So let's say, what is the distance traveled by the particle in first x, that is x. Time taken could be x upon v1 in the first part of the motion, and in the second part of the motion the time taken would be x upon v2. So this would be the total time taken in the motion. The total distance covered by the particle is simply x plus x. So total distance upon total time, x by v1 plus x by v2. Upon calculation you would get this is equal to 2v1 v2 upon v1 plus. A car travels with the speed v naught, this is v naught, for first half of the complete distance. For the next half of the distance is covered with speeds v1 and v2 for equal times within that distance. Find average speed for the whole motion. So it is given that in the next half or in the final next distance, the speeds are v1 and v2 for equal times. So we want to find the time taken for that particular motion. Let's say the distance covered in first half is x, then distance covered in the second half is also x. The times taken in the second half of the motion are t and t, so that is where we want to focus. So time taken in the second half of the motion is t, that is, it is covering the next half of the distance with equal times. So t time v1 plus v2 into t. So v1t would be the distance covered in the second half of the motion plus v2t, since the times are equal. So this should be equal to x. So just revisiting the question what we have done in calculating this and why is it equal to x. What we have done is that we have divided the motion into three parts. So in the first part of the motion, the distance which we are going to cover is x. In the second part of the motion, the distance we are going to cover is x, but that too in equal times, t and t. So we would say that in this t time we are taking the speed v1. So the distance covered in that particular time would be v1t, and the speed taken in this part of the time is v2. So the distance covered in that particular time would be v2t. So the complete distance covered is x, and that should be equal to the sum of the distance covered in individual times. So that means v1t plus v2t should be equal to x. The speed for the first half of the motion is v naught. So we would say that the distance traveled is x. The time taken is x by v naught in first half of the motion. So applying the formula for average speed would be the total distance 2x divided by total time, x upon v naught plus t into 2. So 2 into t, that would be equal to 2x upon v1 plus v2. Total distance upon time in first half plus 2 into time for the second half, which you can draw from here. Calculation the value of t we have used from this equation. So after calculation you would get 2 v naught v1 plus v2 divided by 2 v naught plus v1 plus v2. So this is the average speed for the whole motion. Now, average velocity also contains a vector information within it, so it would have some direction. Since velocity is a vector, speed was a scalar quantity. That's what we want to say. That speed was a scalar quantity. That's why we were not talking about I cap or j cap, or in which we are going to, in which direction we are going to travel. But when we talk about average velocity, then it's a vector quantity. So when it becomes a vector quantity, direction must be associated with it, no matter what. So that is the definition of average velocity. It is simply the ratio of the displacement of a particle in some particular time interval divided by the time taken in completing that displacement. So I hope that the definition is clear. So for one dimension, we want to write what is the average velocity of the particle. So for one dimension, the average velocity of the particle is defined as the final position of the particle minus the initial position of the particle, that is the displacement, upon the time interval taken for that displacement. So this expression is same as what we have learned in class 9. In class 9, we also learned that the average velocity is some final position minus initial position, that is displacement upon time. The definition pretty much remains the same, except that the same concept has to be applied in some wider range of problems. So what is XF? XF is some final position, XI is some initial position, delta T is some time interval, and VAV, that is how we denote average velocity. Displacement and average velocity are independent of the path of the particle. Again, as displacement is independent of the path of the particle, same way average velocity is also independent of the path of a particle. Example. Now in this particular example, a particle follows the path x equal to t square meters. So it is given here, it is in meters. We have to find the displacement of the particle and the average velocity of the particle between 0 and t equal to 2 seconds. So I guess this would be our final example for this particular lecture. Uh, so how do we find the displacement of the particle? Displacement of the particle is eventually calculated by putting the initial and final times. The time, the final time which we are going to use is t equal to 2 seconds. So t equal to 2 seconds, when substitute here, you would get x equal to 4. So that is the final position. Initial position is simply t equal to 0, that is 0. That is 4 meters. So the particle has a space by 4 meters in 2 seconds. The average velocity comes out to be 2 meters per second. So this is the first lecture on kinematics. In the next lecture, we would do the questions in this particular idea, the average velocity, and we would learn how to find the instantaneous velocity using different mathematical tools. So thank you for watching.